Now, when we look at addition reactions, what we see is that there can be differences in how those groups are added, particularly when we're looking at water. And we're going to look at something called Markovnikov's rule, and that predicts how the water will add to an alkene. Now, when we looked at example of adding water to our ethene, our alkene here, notice that the carbon-carbon double bond is very symmetrical in that there are two hydrogens attached to each of our carbon atoms. And so regardless of whether I added the H or the OH to this carbon and the other group to this, the resulting molecule would look the same. Because if I drew this molecule, adding the H to the right carbon and the OH to the left carbon, this is still the same molecule, it's just flipped over, it's just a reverse of that. So these are the same molecule. So it didn't matter how I showed adding the H and OH, I got the same molecule. However, the same is not true when the molecule is not symmetrical. So now, when I look at Markovnikov's rule, it tells me how that water is going to add when I have a situation where it's not symmetrical. And what it tells me is that the hydrogen of the HOH, so we have H and OH, remember that we're adding, the hydrogen of the HOH will add to the carbon with more hydrogen atoms. So when I look at this molecule, which is different because now we have this CH3 group here instead of a hydrogen like we saw in our ethene, what I see is that the carbon on the left has two hydrogen atoms attached. The carbon on the right only has one hydrogen attached to it. I don't worry about the hydrogens that are attached to that carbon. I only look at the number of hydrogens directly attached to the carbon involved in the double bond. I'm going to say that again. I only worry about the number of hydrogens attached to the carbon atoms involved in the double bond. So this carbon has one hydrogen attached. This carbon has two hydrogen attached. The hydrogens in the CH group do not count towards the carbon in the double bond because these hydrogens are attached to this carbon, not this one. So we only look at what's directly attached to the carbons involved in the double bond. And the hydrogen group will add to the carbon with more H atoms already attached. So those hydrogens want to go hang out with their friends, essentially. They want to hang out with the other hydrogen atoms. So we see that the hydrogen attaches to the carbon on the left. The OH group attaches to the carbon on the right of that double bond. So the other option, which would show carbon with my hydrogen here, this compound does not form. It is not favored. A very small percentage might form, but it is not the preferred molecule. And so as a result, we will see this as our primary product. Let's look at an example of what is the product of the hydration of this molecule. We see that we have a double bond and we're adding water, so we know we're going to add that as H and OH. And so because we're adding water, because these are not the same groups being added, we do have to worry about Markovnikov's rule. What we see here at the bottom are the two possible products, because notice in both cases we're adding an OH and an H on either carbon involved in that double bond in the original molecule. And we have to figure out which one is the preferred structure. So the first thing I want to do is I'm going to look at my carbon atoms that are involved in my double bonds, so these two atoms, and I'm going to determine how many hydrogens I have attached to each of those carbons. So looking at this carbon on the left side of the double bond, I see that this carbon already has 4 bonds, therefore it doesn't have any hydrogen atoms attached to it. When I look at the carbon on the right side of the double bond, I notice that it already has 3 bonds, which means it's only going to have 1 bond to hydrogen. I don't need to worry about the number of hydrogens attached to any other carbon atom because the only thing that concerns me are the number of hydrogen atoms attached to the carbons involved in the double bond. I see that the carbon on the left has no hydrogens. The carbon on the right has one hydrogen, and so the hydrogen atom, the additional hydrogen atom of water, is going to go to that carbon atom. Notice that we still show the three bonds here. Remember, there's still another hydrogen there that was already there in the original molecule. We're just showing the addition of the OH. And this will be our correct answer because we're adding the OH to the side, to the carbon side, where there are fewer hydrogen atoms already, in this case none. And I'm adding the hydrogen to the carbon atom where there are already more hydrogen atoms. If we have a situation where there is no way to distinguish between the two, we would actually get a mixture of both products. But when there's a different number of hydrogens, we can predict the preferred product. Answer B is incorrect because it adds the hydrogen to the carbon that has no hydrogens already and adds the OH to the one that has the one hydrogen.